continue talking about our first momentum balance or momentum budget, which is going to be for the vertical momentum equation, that is the acceleration and the direction of gravity. And we're going to use it in a steady state balance, that is when the water's not moving. And so unmoving water is hydrostatic conditions. So this is the hydrostatic balance that we're going to talk about. It's going to be a balance between pressure gradient force and gravity. So first we're going to talk on the big picture about what the momentum budget is like and how it differs from the other budgets that we've been talking about: salinity, temperature, volume, mass. And then we're going to talk about which terms are big in that budget. And that's really the concept of balancing the big terms. Is sometimes called a distinguished limit, sometimes called a dominant balance. But really, we're going to have a lot of these different dominant kind of one term versus another term balances we're going to discuss. This one, the hydrostatic balance, is the first example, where the buoyancy equals the pressure gradient, or force of gravity equals the pressure gradient as well. We're going to see a little bit about buoyancy when we're going to talk a little bit about the Boussinesq approximation. Okay, so the momentum is a vector, not a scalar like salinity and temperature. And so it's it being a vector, it's a makes this equation a little bit more complicated, because instead of an equation for temperature, an equation for salinity, there's an equation for the x direction of velocity, the y direction of velocity, the z direction of velocity. And then this advection term also has an x and a y and a z, acting on the x and the y and the z gradients, all acting on the x and the y and z components of this velocity. So this thing is kind of a mess to think about. Over here, this gradient gives you an x and a y and a z derivative of the pressure. So the x velocity is affected by the x gradient and the pressure, and the y velocity is affected by the y gradient and the pressure, and the z velocity is affected by the z gradient and the pressure. And then you might have other body forces. We're actually going to talk a lot about gravity, which is another body force here today, but we're going to talk about the Coriolis force and centrifugal force, a couple of other things that all are going to end up in this term. But not today. Today we're just going to think about gravity. So where does this equation come from? Well, just like we saw for the salinity and temperature budgets, or volume budgets, mass budgets, you can do a control volume form, you can do a control mass form. There's a translation between the two, which turns out to be a material derivative. This is the material derivative right here of the velocity. So that's where it comes from, getting these two together. But notice now, in this case, the flux, here actually I'm still writing the flux in the mass units, but the flux of momentum would look like rho times u times the u that is the momentum. Velocity goes together with the momentum. So two different u's, and they might not be in the same direction. The transport u needs to go normal to the surface, but you could transport momentum that's in the same direction as that arrow, or momentum that's in either of the two directions perpendicular to that arrow. So there's actually three momentum fluxes to think about going through this face, just like there are three momentum equations here to think about. Cool. So we might compare then the density, which is the mass, conservation of mass equation, to the conservation of momentum equation. So instead of rho, we have rho times u, that's the momentum per unit volume. And then there's this complicated flux of momentum, which is, like I just said, is rho times u in the normal direction, which is the one that matches with the divergence here. And there's also this other one. So rho times uj is the momentum. Look, here's rho uj, and here's rho uj, that's the momentum. Oh, I should say these indices can go over any of the spatial directions. And when they're doubled, like I and I here, it means that there's a dot product. I've also written a dot product here to remind you. But so see the pressure gradients in the j direction, the momentum's in the j direction. If I put this rho together with this uj, that's momentum in the j direction. And then there's also a transport by u in the I direction. complicated. And then you could have the body forces, which would also be in the J direction. Or maybe it's simpler just to think of this as the material derivative, which is a scalar-like object, even though it involves a vector derivative inside, partial derivatives, of the velocity in a particular direction. And oops, you'll notice that there should have been another row here. This one is a little different from this one because you can use this conservation of mass equation to pull the row outside of these two derivatives and to move at the same time move one of the row u's outside. So this should have been, let me pause it and fix this equation. And bingo, we're back and the equation is fixed. All right, so now you might be able to see, if I were to take this equation, I can pull the rho out of the ddt, I can pull the rho ui out, end up with a ui here. So I'd have rho ddt of uj, I have rho ui on this term, and then rho's go over to this side, the ui stays there, there's the material derivative on this side, and then over here we have, oh, missed again. And the third time's a charm. Now we have the material derivative of the uj on this side. Over here, we've got the gradient of pressure divided by density with a minus sign that it should have had. And then the force, body force is also divided by pressure, by density. Okay. So the hydrostatic balance is the balance between this momentum equation for a static fluid now. That means that all the u's go away. The water's not moving. So this one's gone, this one's gone. So we just have this balance between the force, body forces, and the pressure gradient. That's a static balance. If there is a constant gravitational acceleration, it's the body force, then we just get this equation. So the only direction is the vertical direction. Rho g is the constant gravitational acceleration acting on the mass per unit volume over rho. That's rho g, and it's downward, so minus. So d pressure dz equals minus rho g, where g is our regular old 9.81 meters per second squared that we're used to. So you might say, oh, well, let's just integrate this and see, because isn't this right-hand side a constant? Maybe rho, if rho were a constant, then it would just be a linear increase. But in the atmosphere, rho is not a constant. And in fact, we spent all of last class talking about how rho was related to pressure. So let's be a little more careful with that. And we'll get to seeing what those solutions look like shortly. So if we take the whole momentum budget with all of its complicated parts, and here's the Coriolis force we haven't talked about yet, but anyway, and here's the viscosity, which we also haven't talked about yet. But if we take that, hiding inside of it is this little portion, which is the hydrostatic balance, where the rho g in the z direction, the vertical direction, is balancing the pressure gradient. If you go through this in a mathematical sense to say, what is it that makes these two terms the largest terms in the vertical momentum equation? Like, why is this bigger than the vertical velocity? Or why is this bigger than the advection of vertical velocity? Or why is this bigger than the vertical component of the Coriolis force? It turns out that this balance tends to happen whenever the aspect ratio of the motion is small. By small, that means like flat like a pancake. The aspect ratio is for motions that are much wider than they are deep. So like we said in the first day, the paint on a globe is a good aspect ratio for the oceans. They are much wider than they are deep. So on large scale, large and the horizontal scale motions of the ocean, we expect the hydrostatic balance to actually hold pretty well as a description, even when the water is moving. Most of the balances we're going to be thinking about are pretty large scale. So the hydrostatic balance is going to be just sort of taken on all the budgets that we're thinking about in this class. When does the hydrostatic balance get violated is when you get to things that are overturning, like small scale turbulence. That doesn't have a small aspect ratio. It has kind of an order 1 aspect ratio where the height and the width, or height and the length, are about the same size. Well, let's think about how we'd solve this little piece of the equation. So we wrote it down this way before. This is the pressure dz equals minus rho g. Well, what if we just integrate? Then we have pressure equals the definite integral from some z, which is the z at which we're evaluating the pressure, some z0, that's like a standard, some other depth. You could flip it upside down and maybe put that z0 up high, like at the surface of the ocean, the z down. And then we have rho g dz. Well, rho is the mass per unit volume. So rho dz is the mass per unit area. And mass times gravity is the weight. So the weight per unit area is what the pressure is. The weight where? Well, the weight from z where you are up to z, that reference level where we said the pressure would be 0. So if we took that to be the surface of the ocean, having a pressure of 0, or pressure equals a constant atmospheric pressure, then the pressure in the ocean is the weight above you, in between you and that reference level. Cool. And so the pressure at z equals 0 is 0. Or it could be a constant if you wanted. That doesn't really affect this too much, but this is a simple way to do it. And actually in the ocean, the pressure accumulates so quickly that taking the atmospheric pressure as roughly a constant isn't that big of an approximation to have it being 0. So what does it mean, this weight above you per unit area? Well, let's think about a practical example that's going to come back to us over and over again throughout this class. We're going to think about a tall, low density stack of pillows. The weight per unit area is pretty low per pillow, but if you had a tall enough stack of pillows, you can get a pretty sizable weight piled up. Whereas a short stack of bricks might have the same weight as a tall stack of pillows. So we'd have medium pressure underneath each of those. If they were the same height, we'd expect to have lower pressure underneath the stack of pillows. And if the stack of bricks were much shorter, we could actually have low pressure under the stack of bricks compared to the pillows. It's the weight of the air and water above you is the hydrostatic pressure. So at the bottom of the ocean, it's the weight of all the water above you per unit area and the weight of the whole atmosphere above that per unit area. Or another way to think of what the atmospheric pressure at sea level is it's the weight per unit area of the whole atmosphere above you. All these things are things that are useful to get in your brain. Okay, so we went quickly through this before, but let's go back through this again. In the ocean, typical depth about 4 kilometers, we have stratification. And as we go toward the poles, the surface water is getting colder. In fact, but the surface water never gets colder than freezing, which is a little bit below 0 for salt water, about -2. And the deep water is pretty much the same temperature as that surface water at the coldest place. In fact, it's typically the coldest place at the coldest time of year has the same temperature as most of the water in the bottom water and deep waters. So about 80% of the water is in the deep and bottom waters down here. And you start from about 1 kilometer and go down. Then in the upper kilometer, there's a pycnocline where pycno means density, cline means changing. So a rate of change in the density. So this is where the density goes quickly from these deep densities, which are dense, to a surface density, which is lighter. And in fact, the surface zone typically consists of a mixed layer and maybe a transition between that mixed layer and the pycnocline. So that's what we tend to have. The surface zone is also where all the biology lives because it's where the light is. So sometimes it's called the euphotic zone. It's also oxygen is refreshed up there, lots of things like that. We can also think of it in terms of temperature. So the warm surface zone above the rapidly changing temperatures through the pycnocline, which in this case is called the thermocline, because the temperature is changing. And then the deep and abyssal water is less stratified than the pycnocline. And in fact, we saw it may even appear in situ temperature or in situ density to be unstably stratified, but in potential temperature and potential density, it typically is stably stratified or neutral. The pycnocline might also be a halocline. This is particularly important in the Arctic, where you have fresh water at the top having to do with ice transformation, or in the Bay of Bengal, where you have a lot of heavy monsoonal precipitation. You can get a strong halocline. That's the kind of thing that happens in specialized places. Most of the ocean, the pycnocline is a thermocline and a weaker halocline together, and these two are combined rather than in competition. And like I said, we talked about potential temperature versus real temperature, and we talked about stratification. So in both of these cases, the pressure that goes along with this conversion between temperature and potential temperature is the pressure of the hydrostatic pressure at that depth. And then this is just the notations that we talked about before, the sigma notation. All right, so let's do a couple examples of hydrostatic pressure to see how we solve this equation. We solved it just with an integral form, but we can actually write down the real solution if we knew what the equation of state was. So for an ideal gas, the equation of state is rho RT equals P times M, where R is that constant in those units, and M is the molar mass. So rho G equals P over mg RT, which equals P over something that has the units of height, that is a function of temperature. Or looking at it in the differential equation form, dp dz equals P, there's a pressure over here, over something height that's a function of temperature. But if we took an isothermal atmosphere, which isn't a terrible approximation for Earth's atmosphere, then H wouldn't be a function of temperature, it would just be a constant. And so then we can solve this equation. This is something is proportional to its derivative, which is the governing principle for the exponential function. The exponential function is something that is proportional to its derivative. So plugging in a P naught as a surface pressure and Z equals 0, we get this solution. The pressure decays exponentially with a height scale that's determined by temperature, and in Earth's atmosphere, that height scale is about 8 kilometers. So the pressure drops by a factor of E every 8 kilometers in altitude. Now we go back up here and we say, hey, look, that's a constant and that's a constant, and we just assumed that it was an isothermal atmosphere. That tells us that the density of the atmosphere is also dropping exponentially every 8 kilometers of altitude. Which makes sense because up here we had said that the pressure dz, which because it's an exponential, is just proportional to pressure itself, equals the density. So the density has to drop exponentially. If the pressure dz drops exponentially, and if dp dz drops exponentially, then P drops exponentially. So we're all happy. Everybody's exponential in an isothermal atmosphere. What about the ocean? If we had a constant density ocean, we can solve this equation again, but now we just replace density with the background density, the constant value, and then even I can solve this equation, this differential equation quickly. I integrate in Z and I get pressure equals minus rho naught GC, where now Z equals 0 is where pressure is set to be equal to 0. Bingo, that is the solution for the ocean. The pressure starts at 0 at the surface, or you could say starts at the atmospheric pressure, but that's just a constant you add on over here in this kind of simple example. And then it increases as Z goes more and more negative as we go deeper and deeper into the ocean. it increases with the factor rho naught G. And if you plug in what rho naught G is about 1,000 kilos per cubic meter. G is 10 or 9.81 or approximately 1 decibar per meter. If you multiply those two together, that is about 10 to the 4th pascals per meter, 10 to the 4th newtons per cubic meter, or here we go, here's the density form. 1,000 kilograms per cubic meter is rho naught, and 10 meters per second squared is G. So all of these different units are identical. But the one that most oceanographers remember is 1 decibar, so 1/10 of an atmospheric pressure per meter. So every 10 meters, you get another atmospheric pressure. Is there a consistent way to piece together hydrostatic flow, incompressibility, and potential temperatures and end up with the sensible and consistent equations of motion? Yes, there is. It's called the Boussinesq approximation. I'm going to do this very quickly. This is done much more carefully in Valis if you want to go look at it. But basically, the idea is that we allow the density to vary a little bit around one constant value so that it makes it much easier to subtract off the background variations in density and pressure that have to do with that hydrostatic, most of that hydrostatic pressure, and look at just the anomalies from that. So if there are small density changes, we could look at our equation of state, and we'd have a little bit that depends on the pressure, a little bit that depends on the salinity, a little bit depends on the temperature. If the change, the delta from place to place and density is small versus the background density, and if the speed of sound is much faster than GH, this one has to do with the compressibility of the fluid. And that's true if GH is less than about 1,500 meters per second. That's what speed of sound is in water. Or H, if you plug the G over to this side and multiply it out, is less than about 200 kilometers, which the ocean is, because the ocean is about 4 kilometers deep. So it's about 50 times too shallow for this to be violated. Then you get that. You can do the same thing for temperature. How much does temperature have to be? And that works out to the temperature variations have to be a little bit less than about 5,000 Kelvin, which almost surely holds. And if you plug in for the salinity variations in density to be much less than 1, that's true if the variations in salinity are about less than 1,000 PSU. That is the seawater 100% salt? Or 1,000 parts per thousand salt. So pure salt varies on this level, but not seawater. Seawater tends to be from about 40 parts per thousand or PSU to 0 in pure water. Okay, the Boussinesq scaling then says, let's take our density and expand it out to a background part and a little variation. Our hydrostatic pressure then is going to be a background part that's now a function of Z that depends only on this density, and then a variation in pressure that depends on this density. So the hydrostatic part is constant, so that D minus G rho naught gives you this P naught, and that one is so the background pressure is going to be hydrostatic, and the deviation from the background density, this guy, gives us the buoyancy, which is, if you multiply by a G, this is the variation in density divided by the background density. This object has the units of acceleration, and it appears in the equation in a really convenient way. So if we look at the momentum equation and plug in these same units, we see that the conservation of momentum gives us, there's a 1 over rho here, gradient of pressure, here's gravity, plug in for rho plus delta rho, this is the whole rho, that cancels the rho over here. There's a variation in pressure, there's the background pressure, because we're just expanding this one into the 2 parts, so that's a variation part and its hydrostatic part. The hydrostatic part cancels the rho naught part that comes over from here when we multiply through by rho naught plus delta rho, rho naught plus delta rho times g, this orange box cancels out and goes to 0. So the only thing that drives the deviations in pressure, and apparently the deviations in pressure are the only thing that drive the velocity, is this variation in gravity, which is precisely the buoyancy. So the accelerations are driven by the buoyancy plus the gradient of the leftover bit of pressure, the pressure once you remove the hydrostatic part of the pressure. This is almost what you want it to be, except there's one funny tweak, which is that if the depth of the fluid changes from place to place, you could also make variations in pressure from changing the total depth. Because if the weight of the water above you could get heavier because you've changed the density above you, or it could get heavier because you've changed the height of the water column above you. So we have to be a little bit careful about that. We'll come back to that. But the buoyancy in place, those horizontal variations in the pressure, or the variations away from the hydrostatic pressure, those are the things that drive the velocity acceleration. Notice also that in order to have this come over here, we neglect this term, this small correction term, but we don't neglect the variation over here. We can neglect it here because this one is always sitting next to a much bigger term there. So this is like, if we multiply this term by 1,000, it's not that much different if we multiply by 1,003. Whereas this term, because the 1,000 part neatly cancels with this hydrostatic pressure, those two go away, then the 3 is the only thing left over to do something interesting. And the same with the pressure. So where the smallness of this delta rho comes in is in simplifying which density it is that multiplies the acceleration on this side, which makes the buoyancy form only depend on rho naught in the denominator, not rho naught plus delta rho, which is a whole lot more convenient because it makes it linear rather than non-linear. If we go a little bit more carefully through the scaling, now if we go on to the conservation of mass budget, we can take the conservation of mass and relate it into the deviation in rho part, because the rho naught goes away when you take its derivative, and the rho naught plus d rho here, but this is much smaller than that. So it turns out that most of this equation is equal to rho naught divergence of v equals 0, or just divergence of v equals 0. But once we have this being approximately true, we can now go back to this equation and say, what are the small deviations in density away from that? So this does not imply that the density variations are exactly 0. It just implies that they're small. So if we go to write our equations, now one more step. We also might, instead of writing an equation for density like this, we might think about writing an equation for buoyancy. But we know the deviations in buoyancy is the thing that goes with that small density part, but the deviations in buoyancy aren't going to be 0, because we just showed that this doesn't require them to be 0. But where do they come from? Well, they come from the conservation of potential temperature and the conservation of salinity. Put those together with a linear equation of state, bing, 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 or even a nonlinear equation of state that relates buoyancy to potential temperature, salinity, and depth of pressure, then we get an equation that looks like this. So instead of the thermal equation and the salts equation being separate, we could think of it as being a buoyancy equation, or we could keep these two separate and then find the buoyancy using the equation of state to give us the buoyancy that needs to go in our momentum equation. So now we come back to this idea of the buoyancy frequency, and we can play the same game we played last time, but instead of doing it kind of heuristically, we actually can use the vertical momentum equation. So here's the hydrostatic part, here's the acceleration part, here's the background pressure, but now we deviate away from the background pressure by making some anomaly. We lift our water parcel up by a bit z, and we get a change in the rho that goes with it. And so the acceleration has the anomaly between the density at a particular height and the pressure at a different height, or potential density at a particular height and pressure at a different height. You take this, you Taylor series this guy with that guy. Sorry, this is just using the hydrostatic relation to convert this pressure into the equivalent rho g at that same depth. And now look, we've got rho at z plus the delta z. We got rho at z. We Taylor series this guy, and we find that we get an equation that looks like, oh, one more thing. We notice that w here is actually the time derivative of vertical location. So dw dt is really the second derivative with respect to time of this anomaly z. So the anomaly in z goes like g over rho d rho dz, which is the first term in the Taylor series of this that doesn't cancel with that. And that is how we get n squared. And it really should have been rho potential density here if we were being really careful. This still would have been rho background. So that's why we call it the buoyancy frequency, because this the oscillations and displacements in z go with this frequency, n squared. And the minus is what you want to have it be a real oscillation. Okay. So this is the same game we played before, except in that time we came up with g over rho d potential density dz. There's the minus signs there. This is the stability point. You can go back and think about what would have happened if we had gotten the opposite sign of this. It would have been, instead of oscillations, we would have gotten exponential growth away from the small z displacements would have grown exponentially in that same direction. Okay. So the last thing we want to cover is just what's the buoyancy frequency like? What's the stratification like? Let's talk a little bit about pressure and that kind of thing in the ocean. So here is a map from a paper by Monk in 1995 that just gives you a sense that stratification in cycles per hour near surface is about 4 cycles per hour, something like that. So that inertial oscillation is 3 or 4 times an hour, 15, 20 minutes for those oscillations. We go deeper into the ocean, it's about once an hour at about 1,500 meters. And then it's about once every 2 hours, once every 3 hours, once every 5 hours as we get down into the abyssal ocean. So those oscillations, those waves that are going up and down are going up and down pretty slowly, just a few oscillations per hour. This is the buoyancy frequency from satellite, from the state estimate. This is from ECHO at 3 different depths. So here it is at the 117.5 meters, 850 meters, and 3,500 meters. So again, we see the highest buoyancy frequencies at the top, with them about 12 cycles per hour in the tropics, and then less stratified elsewhere, down to about 2 or 3 in the polar regions, and maybe 6 or so in the subtropics. And then when we go deeper, we're down to the range where it's like 1, 2, a half, at about, this is 850 meters. Then when we go down to the abyss, we're down into the maybe half, or right, half a cycle an hour. And I was quickly using these locations of different parts of the world, gyres and subpolar gyres and subpolar subtropical regions. We're going to get very, very familiar with this as we go along. But I wanted to point out that weight of the water above you really appears in the sea surface height in an important way. These red subtropical gyres are high pressure anomalies. They have high sea surface heights. These subpolar gyres, and in fact, the southern side of the Antarctic circumpolar current, are low pressure regions with low sea surface height. And the deviation between them, you can measure actually in meters, and it's about plus or minus a meter. So the surface of the ocean goes up or down about plus or minus a meter from the geoid, and that's what satellite altimeters measure. The transport stream function, that is the vertically integrated transport of mass, looks a whole lot like the pressure field. So that regions that are going clockwise in the northern hemisphere and counterclockwise in the southern hemisphere are the high pressure zones on this map. And regions that are going the other way, this way and this way, are the low pressure regions of this map. We're going to understand this, and the ACC that goes around and around this way is high on one side and low on the other. We're really going to understand how this all works. That's where we're going with understanding the momentum equation. All of this pressure to flow relationship is the underpinning of the geostrophic balance and the spheroidal balance, which are the key aspects of understanding the large-scale circulation of the oceans. We're going to talk a lot about these two figures, which is a similar one. This is one that I made for a paper a long time ago, and then this is the velocity. These two are from a model estimate, so we'll have a sense of how that works as well. If you were to take an altimeter and actually look at the surface of the ocean, you wouldn't see those beautiful gyres. You would actually just see little wiggly eddies that were migrating around, because the variability in sea surface height actually totally dominates the mean. And so we're going to spend a lot of time thinking about this, but where we're really going to be able to make progress is in the time mean, because these little eddies don't have a simple equation that governs them. They all have fundamentally lots of nonlinearity in their momentum equation, which makes them too hard to solve without a numerical computer. All right, that's it. Hydrostatic balance, talking about pressure, talking about density, talking about gravity, talking about how they vary, talking about small aspect ratio motions. That's what we've been on about. This is part of chapter 3. Thanks.